Hey, all right. I got another example for you guys for static equilibrium, and it involves a door. And this one is going to blow a couple of your minds, and you'll understand why when we go through it. Um, it's not incredibly difficult, but something about the result may emotionally scar a few people. Um, so I gotta forewarn you now. All right, I'm joking, but there is something about this example that is going to freak a few of you out, and I'll explain. All right, so anyway, let's say you got a door. Okay, so you just want to draw a rectangle on your page, and let's say it's hanging from two hinges, one there and one there. It's like a bedroom or bathroom door or something like that. And I'm going to give you some dimensions for the door. Let's say the door is 3 feet wide, which is pretty typical for a door. Let's say this here is 1.5 feet from the hinge to the top of the door, and from the bottom hinge to the bottom of the door, same thing, 1.5 feet. And then the center of the door from here to here is 4 feet. So the total is 7 feet, which is pretty standard for a door. And let's say the door has a weight of uh, 80 pounds. So the weight of the door is 80 pounds. Okay. So my question is, let's call the two hinges A and B. All right. So what are the forces acting on the door from the hinges? What forces do the hinges apply to the door? Okay. And there's going to be two components to these forces. So I'm going to label them X and Y for each hinge. And you can make a guess as to which direction they point. So for instance, up here, maybe AX is to the right, and maybe AY is up. And similarly down here, maybe BX is to the right, and maybe BY is up. Now, by the way, if you're looking at that, a couple of you may already know that at least one of these is wrong. All right, because if you look in the X direction, the net force would be to the right. Get it? Right? So you know either AX or BX has got to be turned around. And the only other force acting on the door would be the way of the door, which we'll call W, acting at its center, which is 1.5 feet from the hinges horizontally. All right, so let's start with the X direction. So net force in the X direction is going to be 0. Well, that means AX plus BX has to be 0. So AX equals negative BX. So again, one of those two forces is turned around. We'll figure out which one in a sec. Now, by the way, if you've ever hung something like this before, held something like this before, like if you hold your textbook, let's say where hinge B is, like if you were to grab a textbook or something kind of heavy and put your hand where hinge B is and let the books kind of go, the book will try to go this way. It'll try to go clockwise if you're holding it where B is, which means AX is the one that we guessed wrong on. AX, the hinge A has to pull left on the door to hold it in place. But if you didn't know that, don't worry about it. We'll figure it out. All right, so in the y direction, we know that the force is 0, net force in the y direction is 0. That's pretty easy. AY plus BY has to equal the weight of the door, which is 80. So that's pretty silly, right? But we don't know what AY or BY is yet. We know the sum of them's got to be 80. So we've got four unknowns, right? AX, BX, AY, BY. So we need four equations. So the third equation, we'll do a net torque. Now, as we've been doing throughout, let's pick an axis through which some of my unknowns go. So I'll pick hinge B. So I'll do net torque about hinge B, and I'm going to call clockwise positive here. All right, so BX and BY go through that point, so they don't cause torque. And the AY, its line of force also goes through hinge B, so AY doesn't cause any torque. So the only two forces causing torque about hinge B are AX and W. And the way they're both drawn, they both provide a clockwise torque, which again, you can see one of them's in the wrong direction, and it can't be the weight, so it's got to be AX, right? But we'll stick with our what we guessed, and then we'll get a negative answer. All right, so we have AX. Now, what is its lever arm? Well, it is 4 feet perpendicularly from point B, so this would be 4, plus the weight, which is, oh, and I'll go ahead and put that in. The weight is 80, okay? And what is the weight's perpendicular lever arm from hinge B? Well, that's 1.5 feet. It's half the width of the door, okay? And that all has to equal 0. And so you get AX times 4 equals negative 120. So AX equals negative 30 pounds. Okay, so AX actually points left. Okay, and it's 30 pounds. Well, now we know BX would be positive 30 from this here. So we now know the X components of both the hinge forces, but we haven't found any Y component yet. So we have to pick another axis, net torque about some new axis. I'll put a little Y here just to make it a new axis, has to also equal 0. So I got to pick an axis. Now I have to pick an axis such that either the torque created by AY or BY is not 0. So you have a lot of choices here. It just can't be on hinge A or hinge B. I will pick the center of mass of the door. So, well, actually, I'll make that a Y. So that'll be my next axis. So I'll pick this to do net torque around. Now, remembering, I gotta leave AX this way in my equations. So keep that in mind. You can't turn it around now. You're already halfway in. But anything that's making the door spin clockwise, I'll make it positive. Anything that's making the door spin counterclockwise, I'll make that negative. So from here, we've got BX is trying to make the door spin counterclockwise. So that's negative BX. And how far is it perpendicularly from Y to that force? Well, that's 2. So we got a 2 there. And then BY is trying to make the door spin clockwise. So that'd be plus BY. And it's 1/2 feet perpendicularly from that point, right? And then AX and AY are both trying to make the door spin clockwise, so they're both going to be positive. So we have an AX times 2 and plus an AY times 1/2, and that all has to equal 0. Okay, so we know BX, that's 30. So we got negative 30 times 2. Don't know BY, so I'll leave that alone. AX, we know, is negative 30 times 2. We got AX right there, right? And then plus AY times 1.5, and that equals 0. And you get BY times 1.5 plus AY times 1.5 has to equal 60 plus 60 is 120. And just for kicks, we'll divide everything by 1.5. So you get BY plus AY equals 80. Hold on a second here. Didn't we already write that down right there? That's a problem. All right, so it turns out that we cannot individually solve for AY and BY. You cannot get an actual answer out of this. There is no place where you could do a net torque or net force and get an AY or BY by itself. Oh my goodness. It's a problem that you cannot get an answer to. Now let me explain this conceptually. As someone who has hung doors before, many of them, it turns out the vertical forces on these hinges literally depends on what happens as you mount the door. So normally when you mount a hinge, you drill holes into a frame and you mount the hinge. Well, let's say that here's your door, and let's say you drill the holes such that when you put the screws in, the holes were a little above where this hinge was mounted. That's going to press this hinge downward, and then therefore this hinge will get pressed upward. So in this case, this top hinge could actually be pressing down for all you know, okay? But it literally, these two vertical forces literally depend on, as you're mounting the door, how well you drill the holes, how well centered everything is, and so on. So without actually physically measuring those two forces, you cannot calculate them. All we do know for sure is that the vertical components, AY and BY, have to add to 80. For all we know, AY could be negative 20, which means BY would be 100 up. That'd be a big force. But it literally just depends on how the door is mounted. So I'm sorry if that maybe burst your bubble. That's not every single problem in all of science has an answer, and this is one of them. So it would take an actual measurement to obtain the AY and the BY. So I hope it didn't blow your mind too much, but I do hope that example was helpful and enlightening. And I'll see you in the next one.